Okay, yeah, thank you very much, David. So yeah, I'm Alberto, and thank you all for joining. And I will be indeed talking about the production of gravitational waves in the early universe, and in particular focusing on the production coming from fluid perturbations and from magnetic fields in the about recent advancements and a bit of a quite biased but overview of the topic. Sorry, I think. So yeah, it's kind of it's kind of always mandatory. Yes, of course, you all know that we had the first detection of gravitational waves now a bit more than a decade ago with LIGO with the LIGO observatories in the US, and since then we have had many more events detected. And actually, just this last November, there was the end of the fourth observing run, and with this we have observed now up to a bit more than 300 events from around solar mass binaries of black holes as well as neutron stars. And this is quite exciting, and there has been a lot of developments in the understanding of these compact objects, as well as actually unfortunately we only had one. That's an event of an observation of the gravitational wave as well as the electromagnetic counterpart, but that already gave us a hint of how relevant this can be to understand not only the astrophysics of these objects, but also to put constraints on more fundamental theory of GR, as well as on cosmology. I mean, it gave us a very inaccurate, but a measurement of the Hubble rate, which as we have many more of such events, we can actually, with, for example, next generation ground-based detectors, many more of these events, this can become really a good way to measure the Hubble rates, as well as information on the equational state of the neutron star and much more, which is not the focus of what I will be talking about, but definitely very interesting. And if we go, so just to put this in perspective, the LIGO-Virgo Chiral collaboration frequency range is around the hertz to a few hundreds of hertz in this range, and then also we expect to have better sensitivity in the next decade with next generation ground-based detectors like Einstein telescope or Cosmic Explorer. So if we go into smaller frequencies, what is now planned for the next decade to be launched at the moment is planned for 2035 is the laser interferometer space antenna, or LISA, which some of you probably know about this, of course, which will be a space-based detector of gravitational waves. And this, again, is mostly designed to observe supermassive black hole binaries, signals from supermassive black hole binaries, as well as extreme mass ratio in spirals, white dwarfs, and so on. But what is very interesting is that it can also, of course, be used to detect stochastic backgrounds, and this is what I will be mostly focusing on. And a very particular interesting thing about LISA is that the peak frequencies around millihertz, which will allow us to actually try to understand the signals which are coming, for example, from the electroweak symmetry breaking process. So, of course, there is a lot of cosmology that one can also do with LISA, and that's besides the astrophysics, as well as besides the fundamental physics and GR. So, but again, this in context, we have the sensitivity of LISA around the millihertz frequency, so at a few decades in frequency below the ground-based detectors, and there are also plans for, again, like this is really more like next generation space-based detectors. These are for now just plans of detectors to actually try to cover the intermediate frequencies. And going even to smaller frequencies, what we have is a pulsar timing arrays. And what is being done in pulsar timing arrays is trying to actually observe an array of pulsars for a long duration and try to understand what is the time at which the pulsars coming from these pulsars are arriving. And if one accumulates this the time delay with respect to what we would expect from the pulsars, because as you know, we have a very good prediction of what we expect for example, for millisecond pulsars in the universe. If we accumulate this time delay over very long times, and we take also into account all the possible sources of noise of these time delays, this can be used actually to put some to try to understand if there is a gravitational background on the wave between the pulsar and the detectors, right? So in particular, if we take different pulsars on the sky and we cross-correlate the time delay coming between from different pulsars as a function of the angular separation in the sky, there's a very clear prediction from GR of what we should be the correlator as a function of the angular separation, if this is actually due to a gravitational background. And this is what is known as the Herring-Sams curve. And if we would have, for example, different sources like just noise contamination around the pulsars, then we actually would expect to have different correlation in the sky. So this means that, of course, this time delay can be extremely small. So this is challenging. But if we have an observation of such a time delay, after taking into account different sources of noise, we get rid of those, and the residual time dependence follows a particular functional of the angular separation. Then this is how we can actually try to claim that this is coming from a gravitational background. And this was actually announced in 2023, so now just almost 3 years ago, that there was a strong evidence that there was such a detection, and that it was actually following something very close to the Herring-Sams curve. And this was observed by the different pulsar timing array collaborations, so by the nanograph collaboration in North America, by the PARS pulsar timing array collaboration in Southeast Asia, as well as by the European and the Indian pulsar timing array and the Chinese pulsar timing array collaboration. So this was also quite exciting. So far, there hasn't been like a claim of a detection, but this already has quite strong evidence that this is following the Herring-Sams curve. And it's already putting some constraints on how it would be such a gravitational background around nanohertz frequencies.
Sorry, but I remember that while nanograph actually claimed a strong evidence, PTA didn't. So
PTA, sorry, EPTA you mean, or the international PTA, or
the EPTA? I think.
How
is the story?
No, I mean, within the EPTA, it was also a claim of 3 sigma, but it was less strong as in nanograph, for example. Now the efforts are actually within the international PTA. The idea is to combine all the data from the different collaborations and do the analysis in exactly the same way. Because of course, this claim for evidence, it's also depending on how you're modeling the residuals for the red noise coming from environmental contamination of different pulses, how you combine the different pulses. There's a lot of data analysis that it's.
So this is ongoing.
And this is ongoing. Yeah. This is ongoing and should be in the next few years. And hopefully within the IPTA, all of are precisely trying to understand exactly how to combine all the data and what we can tell after we have everything together. Yeah. Okay. Yeah. So. Of course, this is like we have a very clear candidate for such a signal, which is a stochastic superposition of supermassive black hole binaries, like the ones that we expect to have in the center of each of the galaxies. And when these are colliding, they will also produce a signal. Since we have many of these that we cannot actually resolve them in the sky, then we expect this to be on the form of a stochastic gravitational background. And this is a clear candidate for such a signal, but of course also, and at the moment it's not clear what is the exact origin of this gravitational background. It's also possible that this is indeed a gravitational background coming from the early universe, and this is what I will also be mostly focusing on. So, cosmological gravitational waves, and precisely it's like we have processes leading to the production of gravitational waves in the early universe. We expect to have a gravitational background that would be of cosmological origin. And as you know, gravity is the weakest fundamental force, and this has a very big disadvantage that it makes it extremely difficult to detect. But at the same time, it is very interesting because it means that whenever such a gravitational signal has been produced, then the gravitons would propagate almost without any interaction. So therefore, they would be freely carrying very clean information of the source. So this means that if we observe this gravitational background from early universe, we are going to be able to go much beyond the CMB. So this will actually provide us with direct information on very early universe physics that is not accessible via electromagnetic observations, and that also can be complementary to to collider experiments. And here it's just some tests. For example, we have a first order phase transition for a particular model. I don't remember which is the exact model. But basically, we can see what would be able to observe with LISA, for example, and compare it to a parameter space that is probed by the high luminosity LHC. So some of these points, they can be tested, and some of them cannot be tested. But as you can see, there is some complementarity between LISA and collider experiments. So this is, of course, quite interesting. And to put, so just to summarize about what we expect from the early universe. So we can have signals of gravitational waves coming from the period of inflation, for example. Then as the universe repeats, then this can also lead to gravitational waves. And once that the universe has reheated and it will start then expanding and cooling down, we expect it to go through some phase transition processes. So at the electroweak phase transition, so around 100 GeV, then the electroweak symmetry is broken. And this is mostly what I will be focusing on, because depending on how this symmetry breaking process occurs, then we expect to have we might expect to have a strong signal coming from this that would be detectable by LISA. Then as the universe keeps on cooling down, then of course it also goes through quark confinement at the QCD phase transition around 100 MeV. And if there is a signal produced around this scale, then this would be also peaking at the frequency of around nanohertz. So then this means that we can use partial timing arrays to try to put constraints on signals coming from QCD or to make a detection. So based on which temperature scale these gravitational waves are being produced, we can make an estimate of what we would expect to be a characteristic frequency, which follows this relation. So as you can see, for a temperature of around 100 GeV, as I was just mentioning, then this would give us a peak sensitivity around millihertz, where we have actually the peak sensitivity of LISA. If the signal is coming from around the QCD scale, then this would be actually peaking around nanohertz. So we can try to probe this with partial timing arrays. And if we go into larger energy scales like a Peche-Quinn symmetry breaking, barium minus lepton asymmetries or left-right symmetries, so some high energy phase transition or symmetry breaking, then we can actually, if this is around 10 to the 7, 10 to the 8 GeV, then this would be probed by ground-based detectors. So at the moment, there is some constraint from LIGO Cairo, but there is not an observation of a gravitational background. But as we go into better sensitivities with Einstein telescope, then it is possible that we actually observe some gravitational background that then could be a hint of such a signal in the early universe. Of course, if we want to explore, for example, GAT scale, then this would be at much higher frequencies, and that's there are some efforts to think of ways to detect such gravitational waves, but at the moment these seem to be the sensitivities are several orders of magnitude above the BPN limits. So that's it's an effort that maybe in the coming decades it becomes more and more reliable. So so just to give you a hint, as I was mentioning, so we have a signal, for example, this is just signals coming from primordial turbulence, so from spinning the plasma at a particular temperature scale, which is what I will be talking about. So if this occurs at around 100 GeV, then you can have a gravitational background that would be then within the sensitivity of LISA. So then this could be detectable. Of course, here we'll have many more sources of gravitational waves, so one needs to really understand very well what to expect here if you want to then disentangle with different sources, as well as with astrophysical sources and astrophysical foregrounds. You can see the current observations by partial timing array. This was from the 12.5 years on nanograph in 2020, actually. So now it's a bit updated. But the point is that if there is a signal produced around the QCD scale, then this would also be completely compatible with the signal, as well as a stochastic background coming from supermassive black holes.
Would you expect this signal given that QCD is a crossover?
I will talk about that, because here I'm being quite agnostic of what is this signal coming from, and I will be first focusing on first order phase transitions, but around the QCD scale, what you could also have, which I will talk towards the end, what I have in mind at least, what I find a potential source for this is if you have a if you have an interaction between for example, the QCD axion and electromagnetism, you can have an amplification of of a magnetic field around this scale, which could lead to turbulence. And this would be well, that's also BSM, but you would actually not need the first order phase transition if you have such a. And that's at least what we were having in mind in some of these papers, where we were trying to put some constraints on the primordial magnetic fields and on primordial turbulence. So if you have a first order QCD phase transition, then you would also lead to such a signal. The point though is that you actually require a characteristic length scale very close to the Hubble scale for it to be detectable. So if you want to actually have something that is compatible with PTA observations, then it needs to be very close to the Hubble scale, which of course it can be challenging to have such a situation. But
so yes, I was going to ask you about F star. So this is a measure of how big the bubbles are.
Yeah, this is the characteristic length scale in this case of the characteristic length scale of the turbulence, but it's if this is induced by a first order phase transition, it's the mean size of the bubble roughly. So yeah, in this case, it's around 100 bubbles per horizon, and in this case, it's around 1 bubble. Okay, this number, of course, can be 1 to 15 or to 20, but
assuming it's close to 1, it's very, very fine too. No?
Yeah, of course. Yeah, this is just taking our models and pushing the limit of the parameter space.
What's the pale blue line there?
This is just a concept for mu Ares. This a concept of a giant LISA for Voyager 2050. It's very far in the future. Yeah. Okay, good. So yes, I will be mostly focusing in the first part of the talk on first order phase transitions and on fluid perturbations due to first order phase transitions. So let me just briefly mention what I'm referring to. So we have a first order phase transition whenever there is a barrier that is appearing between our false vacuum and the true vacuum, followed by another parameter. And if this would be actually a second order, right? Then the false and the true vacuum are not separated by a barrier. So, or if it's and then in this case, if the temperature cools down, we initially have a zero BEF of the scalar field, and as the temperature cools down, then eventually we get our new our true vacuum where the symmetry is broken, and then the scalar field would just transition towards its true vacuum smoothly. But if we have a first order phase transition, then the appearance of this barrier between the false and the true vacuum means that at the moment that we have degeneracy between the false and the true vacuum, then we start to have a non-zero probability of nucleating or breaking the symmetry and going through the barrier to the true vacuum. And if this and since this process will happen randomly, then we expect to have random nucleation of these bubbles of the broken phase with the in the universe, and then these bubbles could start to expand, and then they could start to collide with each other, and this would lead to the and this is the main mechanism that I will be discussing of production of gravitational waves. So you might wonder, of course, why are we considering a first order phase transition, since I was talking about electroweak or even about QCD, and I will not enter into QCD. But indeed, within the standard model, as you may know, the standard model predicts a crossover for the electroweak phase transition for the measured BEF of the Higgs boson around 120 GeV. But then this means that the electroweak cannot account for baryogenesis, because for baryogenesis we actually need to satisfy Sakharov conditions, which can be satisfied in general if we have a first order phase transition. So there are many extensions of the standard model that could lead to, in some range of parameters for some of them, but they can lead to first order phase transitions. And this is kind of one of the strongest motivation to be considering first order phase transitions, because then in principle, of course, depends on which particular model and in which range of parameters, we can also try to account for baryogenesis at the same time as having the first order phase transition, and then we can try to probe with gravitational wave experiments, like in this case with LISA. So once that we can claim that we expect to have a first order phase transition, which then also this means that such a detection of a signal in general, this would lead to actually be probing DSM physics. Then let me now focus on the hydrodynamics of these first order phase transitions. So as these bubbles are nucleated, and then they will start to expand, they will also there will be some interaction between the scalar field that is confined to the bubble wall, in this case determined by the black line. And as these bubbles are expanding, then if we check, for example, in the Boltzmann equation, we can observe that there is a force coming from the rate of change of the masses of the particles due to the interactions with the Higgs field that is exerting a friction into the expansion of these bubbles. So if we check the conservation laws for the stress energy tensor of the fluids, then we have such a friction that will try to stop the bubble actually from expanding, and there can be a balance between this friction and this pressure. And how we model this usually is that then we can expect that there will be a distribution function for each of the particles that we can split into an equilibrium and an out of equilibrium. And this is a huge area of research. People are really trying to understand what is the within local thermal equilibrium, what is the expected wall velocity of these bubbles, so like how fast do these bubbles expand, and if they would actually reach some terminal velocity in which the friction and the pressure are reaching the same values, such that there is a stationary solution to this expansion. It is also possible that these bubbles never get to stop due to the friction in what is known as the runaway regime. But in such cases, then we don't expect the energy transfer between the scalar field to the fluid to be very significant. So I will be mostly talking about the case in which the bubbles reach a terminal velocity, and then there is a transfer of energy between the vacuum energy to the fluid. And this is what, in general, we expect for electroweak phase transition. But again, this is really model dependent, and one needs to check model by model, and it's a huge
when you say the particles, what do you mean? So you mean the rest of the standard model covers to the...
Yes, all the particles of the standard model, or in BSM extensions, then all the... Yeah.
But you're thinking about some BSM.
In general, yes. That's why this is really depending on which model you are thinking about and how they are interacting with the Higgs field, with the second Higgs field, with any other. But this is the general picture, and then we have a conservation for both the stress energy tensor of the scalar field and the fluid, which needs to be conserved, so we can try to solve for the equations of the system of the scalar and the fluids. So if these bubble walls reach a terminal velocity, right, which is the case that I will be mostly focusing, then we expect to perturb the fluid around the bubble. So this first circle is the bubble wall, and we can have three types of solutions depending on what is the velocity of the walls as the bubbles are expanding. So if the bubbles are expanding at the velocity smaller than the sound speed, then what we expect is that we are only perturbing the fluid in the front of the bubble walls, which is the green area, is the fluid which is perturbed around the bubbles. So then these bubbles are expanding, and then they can perturb right in front of them. If the bubbles are expanding faster than the speed of sound, it is possible to be actually perturbing both inside and outside of the bubbles, depending on what is in particular this wall velocity. And when this wall velocity goes above, goes above the Jouguet speed, which can be determined and will depend on the strength of the phase transition. But if it is larger than this value, then it is the limit in which it is not possible to perturb anymore the fluid in front of the bubble, and this is known as a detonation, which has been most. Of course, these detonations and deflagration have been extensively studied in combustion, for example. And in those cases, we will not have hybrids since there is not an energy injection as what we have in a first order phase transition. But yeah, in general, we can have these three types of solution, and this will depend basically on what is the wall velocity, as well on what is the strength of the phase transition, parameterized by this parameter alpha, which is the rate of the vacuum energy to the radiation energy of the universe. And then depending on this, then it modifies the Sherman-Jouguet speed, which right here. So as these bubbles are expanding, now I'm still focusing on only one bubble, then you can perturb the fluid either in front of them. This is the profiles that you would expect for different wall velocities, or you can, for example, for the deflagration cases, you're only perturbing the fluid in front of the bubble, and this is the wall velocity. And if you have a hybrid, then in these cases, you're perturbing the velocity in front of the bubble, but also behind, which in this case very small, but in this case is more clear. And if you have a detonation, then only the fluid part is actually modified inside the bubble. So we have recently put a Python package, which if you're interested in this type of signals, as well as on the gravitational wave diagrams, you can just use pip install cosmological and check the documentation to actually produce these 1D profiles, as well as the gravitational wave diagrams that I will be presenting in a moment.
Is the perturbation behind the deflagration will strictly zero, or is it actually some sort of exponentially small tail that does actually go to zero?
It does exactly go to zero, but this is, of course, this is because we are really considering that the wall it's much smaller than any fluid scale. In reality, of course, what you have is a smooth transition from zero to some particular value, but this scale it's maybe several orders of magnitude smaller than the size of the bubbles, or than the. So yeah, in reality, you have a smooth transition between on the fluid profile, but it's mostly treated as a discontinuity. So then it goes exactly to zero, right inside the bubble. So now putting this in the context of a simulation in which you actually have many of these bubbles expanding, colliding, and leading to the production of gravitational waves. This has been studied by in pioneer work in 2013 by Mark Haimarsh and collaborators, in which they were solving for the system of equations that I showed you before, for like the scalar field together with the fluids. So of course this comes this is quite challenging computationally, because exactly as you were pointing out, we have a very large separation of scales between the size of the bubbles, which can be of cosmological size. It can be a fractional size of the horizon, for example, like 10 or 100, depending on how many bubbles you produce in a phase transition. And then you also need to resolve the scales of the wall, which is of the order of the mass of the peak. So then this is like a huge separation of scales. So this is very challenging. And initially, this was mostly done only for weak to intermediate phase transitions, so like for small values of this alpha parameter. And then what was mostly found in these simulations is that once you have collision of these bubbles and you check what is the fluid perturbations coming from this, you're mostly finding that this is a superposition of sound waves. And sound waves, of course, is the solution that we expect to have in the linear regime of fluid perturbations. So based on this idea is what was developed by Mark Haimarsh and collaborators, known as the sound shell model, which is a semi-analytical model to prescribe what would be the gravitational background coming from these sound waves. So basically, the main assumption is that you have a superposition of sound waves as your solution to the fluid perturbations. You check what your 1D profiles to understand what amount of energy is transferred from the vacuum into the plasma. And then you can make a very clear prediction of what is your gravitational wave background, which you have some efficiency coefficient. This becomes proportional to the kinetic energy density squared, some suppression factor, which I will describe in a moment, and then proportional to also a length scale of the bubbles. So within these assumptions, then we also expect to have two scales. One scale is determined by the mean size of the bubbles, and the other scale is the one that is coming from the thickness of the fluid shell. So these are the two characteristic scales, and it's actually exactly what we find in the gravitational spectrum, these two scales. In a paper with collaborators, we were trying to understand a bit more about the sound shell model, and we actually found that you also have an additional scale which depends on the duration of these sound wave regimes. So basically, we have these sound waves which are present there, and they are only dissipated by viscosity, which is extremely small. So this takes very long times to dissipate. So you can almost assume that this is a steady source of gravitational waves, that it's that is mostly eventually damped by the expansion of the universe, and this is what this factor takes into account. But this kinetic energy, you can take it in the sound shell model, you take it just as a constant. So you are just producing gravitational waves proportional to the duration of the sourcing until this is cut down by the expansion of the universe. However, this is of course not completely the full picture. So what we expect is that this linear regime eventually would develop nonlinearities at a time which is, in these cases, for weak transitions, it is very long. But for strong transitions, this can be much shorter. And this is then what we have so far within the LISA collaboration, for example, when we try to do estimates of the gravitational background. We generally assume that there is a duration of this sound wave regime, and then until that time, and then it kind of saturates at the moment that this develops nonlinearity. So this is kind of our way to model for nonlinearities so far.
So long and short mean what compared to?
Sorry, no.
You said if the transition is weak, the time for attenuation is long.
Yeah.
And if it's strong, it's short.
Compared to one Hubble time.
So it can be shorter or longer than Hubble time.
Yes. In these cases, right? So you can check. So for small durations compared to the Hubble time, then this basically becomes linear in the source duration. So initially it is just linear, and when this becomes of around one Hubble, well, or a bit larger than one Hubble time, then this just becomes a factor of one. So it eventually saturates. So basically, you have a function like this, right? So which you can treat as linear in the short duration. But this final time depends on how nonlinearities develop, which is what I will enter into a moment, and how we understand a little bit how nonlinearities develop. But basically, this is like a scale which depends on the kinetic energy and on the characteristic length scale. So as you increase the strength of the phase transition, the kinetic energy increases. Well, sorry, inversely proportional to the kinetic energy, right? So as the kinetic energy increases, then this duration decreases. So we expect to develop nonlinearities at much shorter times. So this can happen much earlier than we reach this regime in which we just set it to be flat, right? So, and it can also have other impacts in the gravitational background.
Sorry, can I ask you?
Yes.
Sorry.
Yeah, please.
You have a specific assumption for the energy density and pressure inside and outside.
Yes. Yeah.
It was in the next of the previous.
Yes.
So this is the bug model. No?
This is all that I'm now describing is within the Bach equation of state, indeed.
What do you expect? I mean, this is not generic, of course. So if I'm going to change that, I'm going to change all the examples.
Yes. Yeah, that is completely true. So
why do you think this is an interesting case?
Yeah, that's a good point. So if you change your equation of states, right, basically what you're going to change also is the conditions at the boundaries. So you will end up changing the fluid profiles. So that will change the fluid profiles, and what will change actually is in the end your amplitude and the position of these two peaks. But here we're kind of trying to understand, right? I mean, once that you have such a model, how that translates into a gravitational background. So in that sense, this is kind of generic, right? This type of system. But of course, to determine these two peaks, it is depending on how your 1D profiles are. And for that, you need to know your equation of states. And this is only within the Bach equation of states.
So you had some physical, let's say, model in mind that could give you the Bach model and transition.
Yeah. Yes, I will actually. This is exactly the next slide. Yes, but yeah, that's a very good point. Yeah, I didn't mention it, but indeed, all of these results, and I mean, also when we try to do parameter estimation for phase transitions, we're trying to do it with the simplest model as possible, because you could, of course, start playing with any type of equation of state and so on, right?
But to measure something, so
exactly. Sure, of course, yeah. And that's why we are interested indeed into understanding if once that you have your 1D profiles that you can compute for any equation of states, how does that translate into the gravitational background? Which depends, in this case, also will depend on other things, the development of nonlinearities and so on, but it will also depend, of course, on your particular equation of state. Okay, yeah. So yeah, indeed, what we found here is that you also have a bit of more complex structure than initially thought. So these black lines is the initial what was proposed originally, and in reality, what you can have is an additional slope of linear slope, and then that eventually becomes f cubed. So this becomes a little bit more richer phenomenology that one could try to understand. It might not be too relevant because this is really below the peak. So it depends, of course, on how good we can actually observe these signals. But this is also a way to add an additional parameter that then would depend on the duration of the source. So it can also depend on the nonlinearities. And this can affect the shape of this gravitational wave background.
These curves are the result of a numerical simulation.
These are the results of the Sunshine model, actually. Of the Sunshine model, but in the original paper, there was there was an additional assumption on how to do the numerical integrals, but within the Sunshine model, that we show that they were not correct as you go into the infrared part of the spectrum. And when you incorporate that, you have actually two contributions. So one that is roughly like this, and here it decays, and this one that they computed initially. So then the final gravitational spectrum is kind of a superposition of two contributions.
But do numerical simulations support this?
Okay. Yes.
The Sunshine model is just a model.
Exactly. Yeah. The point is that in this range of frequencies, there is no numerical simulation that has a lot of dynamical range to actually have a clear understanding of this part of the spectrum. So when the Sunshine model was proposed, it was mostly trying to find what happens in these around the peak, right, and these slopes. So it is not completely clear, of course, and one needs to compare it to the simulations. And yeah, yes, please.
You might have said this and I missed it, but you said there's two contributions that go into kind of creating this shape that we see. What are those two contributions?
So yeah, they come from. I mean, they come from in the end from product of trigonometric functions. When you take the unequal time correlator of the source, in this case of the sound waves, and basically one of these terms is the one that dominates, and it was taken into account in the original paper. But then you also have actually three more contributions. Two of them are equal to each other, and it gives you something here, and the other one is negligible always.
I see. So it's not two different types of physics that are.
It is exactly the same physics. It's always within the unequal time correlator that you have for the sound waves. But yeah, so there is no additional physics. It's just the same model. So yeah, of course, this is something we are trying to do also to test it with simulations. And actually, sorry, it was actually tested with simulations as well, and this part, but not for the dynamics of phase transitions. But this was tested if you just assume you have an initial velocity spectrum which is purely compressional, and you let that evolve with time, then it leads to such a signal also, and then you can see this part of the spectrum much more clear. So it's not that doesn't mean that this is exactly what you have in the dynamics of a first order phase transition, but it is due to the compressional nature of this source of gravitational waves. So on the fact that you have purely sound waves or acoustic motion.
And what do you say that sets the scale for this peak on the very left?
Yeah, this is quite small here, but this is the inverse duration of the sound wave regime. So when you stop sourcing it, so it means that if it's sometimes you start developing nonlinearities, then of course what happens is more complicated. So it might just not saturate, but at least if you stop the sourcing at some time, right, then it would lead to this third scale that is the small frequencies.
So is it correct to say that the higher peak has to do with the correlation length in the plasma, and the one to the left is the correlation time?
Exactly. Yeah. Exactly. So in a way, yeah, and that's the point that precisely it's important for what I'm going to discuss next, because what we are now trying to do is to understand these two scales, because these two scales are mostly related to your hydrodynamic profiles, while this scale it's mostly it is much more universal, and it's just determined by how the source ends up decaying. So not so much on how is the particular scales that come into the 1D profile. So they are in a way separated, right? I mean,
is that clear? Because what sets the fluid in motion is the initial. You could in principle predict the fluid velocity once the bubbles are gone, fluid velocity distribution, if you knew the profiles of the individual bubbles, statistically. So it's not clear that they are really independent.
No, of course they are not independent, but this will mostly only be determined by the amount of kinetic energy, right, or by the amount of non-linear motion that you eventually have.
But that depends on the profile of the bubbles nuclei.
Yeah. But it depends. What I mean is that it depends on the integrated 1D profile, not so much on the particular scales that appear in the profile. So Yeah, of course, it ends up depending on that. But if you have, for example, so what I mean to say here is that this is really a way to the observation of these two scales is really a way to disentangle certain parameters, right? If you only have one scale that is only determined by the total kinetic energy, then you have degeneracies between alpha and B-wall, for example, right? Because then you could have two profiles that are different, but then they lead to the same kinetic energy, which, okay, all of this is what we're really trying to understand the moment you go into nonlinearity. So of course it's not completely clear, but okay, yeah. So, but this is what is for the moment kind of the state of the art for how well we understand this production of gravitational waves within the linear perturbations in the fluids. And in order to go into the non-linear, sorry, actually I wanted to mention one more thing. So in a very recent paper, together with my PhD student and with collaborators, we are precisely trying to understand what are these two scales, because in general they are mentioned that these are like the mean size of the bubbles and the sunshot thickness. And what we found in this paper is that they are of course related to that, but we actually find indeed these two scales when we try to study the velocity spectrum. Then we find these two scales. One of them is determined by the positions of the front and the wall of the NCS. So these are just the two positions that we have where we have these continuities. And the second scale, which was in general associated to the sunshot thickness, so to this thickness, actually we find that that is determined by the separation between these continuities. So that's interesting, because if you actually try to take, let's think of this hybrid of psi 0.7. If you check the position of the front and the back, which is at the sound speeds, this is actually much larger than if you take the position of the front and the wall, where it actually represents the second discontinuity. So what we find quite clearly here in our analysis is that this is actually depending only on the difference between the discontinuities. And these locations is exactly what determines this second position. So now these are the two scales appearing in the velocity spectrum that eventually translate into the gravitational waves, and that's a work in preparation that we are having at the moment. And what we found actually is that there is a way to predict analytically what is the exact amplitude of this branch, which here is just normalized at 1, but like the amplitude when k goes to 0, the amplitude when k goes to infinity, which is directly connected to the appearance of these continuities, and the position of the two breaks. So once that we have this information, so set 1 and set 2, which end up translating into this k1 and k2, we are able to make an analytical prediction of exactly what is also the intermediate slope. So this gives us kind of all the information we need to know in order to understand what is the position of the breaks on the gravitational spectrum, k1, k2, and the intermediate slope. So yeah, so I mean, this is what we're trying to understand, and in the next paper we will actually put this for the gravitational waves. So far we're just investigating the original velocity spectrum, that is the one that is sourcing gravitational waves. Yeah.
You seem to be saying that initially these perturbations are linear, then eventually they may become non-linear.
Yes.
Why are they linear to begin with?
So they are linear initially because the perturbations are small on the fluids for small strengths of the phase transition, and initially you have you have a spherical configuration of the bubbles, right? So as they are colliding, you are initially just inducing compressional motion into the fluids. So there is no vertical motion at all, right? And this is just coming from the sphericity of the bubbles at collision. So unless there is unless the strength of this fluid is strong enough to develop nonlinearities and vorticity, this is just going to remain compressional for a very long time.
The strength of the transition, you would expect that.
You would expect vorticity to develop, and then you would expect also turbulence and nonlinearities.
Or earlier.
So yeah, this is something that is not completely clear. So I think that upon collisions, you can start producing vorticity because you have a misalignment between gradients of the pressure and gradients of the energy density. So you have a baroclinic term that can lead to the production of vorticity, on top of the usual assumption that you will also develop nonlinearities at later times. So But it depends on how strong is this phase transition. That's, for example, why in simulations I will present, but also in the group of Helsinki, what we're all finding actually is that for deflagrations you have much larger amount of vorticity, because in that case you are actually colliding the fluid shells, and you have regions in the fluid perturbations in which you are in the broken phase and regions in which you are in the symmetric phase, and that leads to these misalignments and to the production of vorticity. But this is still not completely clear. But we were trying to investigate this with some simulations.
Oh, sorry, I understand that inside can be linear evolution, but by definition of a bubble, I mean, if I see from inside to outside, this is not linear. I mean, I'm going to different values. I cannot get by a linear perturbation. So at least close to the boundary of the bubble, there should be some nonlinear effect, or no?
I'm not sure I understand. So I mean, I'm talking about linear perturbations in the linear fluid perturbations here, though, right? So it's the transfer of energy, right, leads to small kinetic energy in the fluids
Inside the bubble.
Inside and outside of the bubble, depending on the type of solution, on the wall velocity. Yeah, around the bubble. Yeah.
When I go close to the boundary, do I not have some nonlinear? I mean, because of this transition from inside to outside, I would expect some nonlinearity happening.
No, I don't think so, because still, I mean,
I'm saying I'm far away from the boundary, so it's me. But there, because I have these two vacuums, let's say, they are not connected by linear perturbation theory. I would imagine that some nonlinearities, I mean, the nonlinearities there should be important. I don't know how they can damage the linearity of inside and outside. I don't know, but.
Yeah, I mean, I don't think so, because in the end you have a very large separation of scales, right? So basically you are treating the fluid perturbations right outside of the bubble and right inside of the bubble, and matching them through a conservation of energy momentum across the bubble, right? So at both sides you have small fluid perturbations, and then you're in both sides of the bubble in the linear regime of fluid perturbations.
You have a amount of energy density.
Yeah.
Which is large.
No, it's actually small.
It's small.
In an electroweak-like transition, it's small because the Higgs is the only one that jumps, but the rest of the degrees of freedom are essentially massless at that temperature. So it's just T to the fourth on both sides.
So this
I mean, the gradient is large, but the change in the.
Yeah, because it goes like T to the cube, the value of it.
But I mean, check in here, for example, right? I mean, you still have.
No, that's a typo.
This is a typo.
And in the first equation, it's T to the fourth.
Yeah, of course.
Okay. Then that's fine.
Okay.
Sorry.
So
I'm not fixated on this.
Okay,
I'm sorry. Yeah. This is of course T to the fourth. Yeah.
But maybe another answer to your question is that in his description, the world is a zero locus, is a zero measure locus. It's a discontinuity. So everywhere else,
so it's a delta function source. So
so everywhere in the volume, is assuming the perturbations are linear.
Right. So it's just a boundary. Let's say
it's a boundary condition.
This is I think. So this is beautiful.
Yeah. Good point. Yes, please.
If the perturbations originally are small, to grow nonlinearities, you have to have a time that is at least 1 over the amplitude.
Yes. Yeah. It's 1 over this kinetic energy and with the length, the 1 over the length scale.
So that has to take a very long time.
Yes, if the perturbations are small, it takes a very long time, and that's why in the small perturbation regime we are mostly using this model to predict what is the gravitational wave background. But indeed, when we go into interesting values of the strength of the phase transition, then we need to account for nonlinearities, and that is when this time might actually not be that large. And if we want to actually have something detectable, we need to go beyond this and to actually have nonlinearities. Okay, which I will now discuss, and I think a bit out of time. But yeah, one main complexity of these type of simulations is that you need to resolve both the scale of the fluid and the scale of the bubble wall thickness. So this limits a lot what you can do computationally. And based on this idea, it was proposed by a group at DESI, by Ryusuke Jino and Thomas Constantine and collaborators, to actually integrate out the Higgs field and run a simulation only on the fluid dynamics, mostly under the assumption that these bubbles are going to nucleate and then they're going to expand and they reach a terminal velocity. So therefore, you can already prescribe which parts of the universe are in the broken and which parts are in the symmetric phase. And just by modifying the equation of state inside and outside of the bubble, then you can solve just for the fluid dynamics and you get rid of the scale of the bubble wall. So this is a very powerful way to solve for these phase transitions, as long as you don't have effects as, for example, the slowdown of the bubbles that has been observed in some full fluid scalar simulations for very strong deflagrations. That cannot be modeled within the Higgsless. But as long as these bubble walls are kind of not being modified, its wall velocity much as they are colliding, then this is a perfectly valid description. And within this approach, together with the people at DESI, we actually were running some simulations of the Higgsless for strong phase transitions up to a value of 0.5. So we are able to present the gravitational background for the first time for such strong phase transitions. And here you see some snapshots of these simulations. So you can see the velocity, the enthalpy, and vorticity. So for example, here you start seeing some vorticity produced in this type of systems. And that's precisely when nonlinearities kick in and become quite relevant. And they will have an impact also on the gravitational background, which is what I will describe in a moment. So
you seem to identify the appearance of vorticity with the appearance of nonlinearities. Is that?
Yeah, because it's nonlinearities. I mean, if you have initially purely compressional, right?
What do you mean by purely compressional? You mean that
so
less
vorticity is 0, right? So I mean, if you have
velocity.
Exactly. So I mean, the curl of the velocity is 0, right? Which is what you have for a spherical distribution. So if your initial fluid perturbations are compressional at the very initial time, you're not going to develop vorticity unless you have nonlinearities. So if you are developing vorticity, in the end, that is it's a consequence of nonlinearities in general. So yeah, that's why I'm doing this connection. And in these simulations, right, we are testing for different values of alpha, of the strength of the phase transition. And for example, here you have the evolution of the kinetic energy. So in the case of weak phase transitions, and this for different values of the wall velocity, we find that the kinetic energy is mostly constant. Here it is decaying a little bit. We kind of not completely understand, but we understand a little bit why this is decaying. But in this case, it's mostly constant. But as we increase the strength of the phase transition, we start to observe a decay of the kinetic energy. And this is also a consequence of developing nonlinearities, because as we are developing nonlinearities, then we can start having the transfer of energy from large into small scales, and then at small scales the energy will be dissipated by viscosity. So then this dissipation of the kinetic energy becomes much more efficient, and actually is what we observe as we go to values of alpha 0.5. Then from this time determines when the percolation time, so when most of the universe is already in the broken phase, and by this time we already are starting to see a very strong decay of the kinetic energy. So this changes quite drastically what we expect compared to the soundshell model, because in that case we are assuming that the kinetic energy is constant.
So by kinetic energy, you mean the non-relativistic concept, or what do you mean by kinetic energy?
No, the relativistic kinetic energy as well. So it's the
what is that?
Enthalpy v squared. So it's in T00. I mean there's energy tensor, right? The energy density you can always split it into internal energy and kinetic energy. So when you don't have any fluid perturbations, you only have homogeneous energy density, for example, right? And then you have a split between kinetic and so it's enthalpy.
That's just leading order in the velocity.
No. That's generic. That's generic. Yeah.
Okay.
I can just tell you how we define it, but yeah.
Okay. And then this dissipation you observe, is that because of the formation of shocks, or is it because of the microscopic viscosity? What is dissipating?
So dissipating is always a viscosity, right? Also when you have shocks, right? The dissipation of shocks happens through viscosity.
No, but shocks can dissipate even in ideal hydro where there's no viscosity. So in ideal hydro, the only way to dissipate is through the formation of shocks.
Yeah.
If you have viscous hydro, then you can dissipate without shocks.
Yes, exactly. But I mean, even in ideal hydro, it's because you always are assuming finite shocks, right? Which in the end, you're going beyond the ideal hydro at the length scale of the shock, right? So in the end, it's the same. Yeah. But here is at the moment unclear. I mean, we are just observing this kinetic energy. Now we're trying to understand a bit better exactly how turbulence develops and what is exactly the transfer of energy. If we can clearly see a forward cascade or a cosmological spectrum in the velocity, but it's not completely clear. So in the end, yeah, it's happening because of this viscosity, and we can clearly see how, as we go into large alpha, then this happens. Then this happens because of nonlinearities, which can be because of the transfer of energy to small scales, and that can happen through shocks or just without shocks. But actually, in the simulation, we observe shocks forming everywhere. So it's
that slope is basically given by the shear viscosity of the system.
This slope is what, sorry?
Basically given by the shear viscosity, or
this slope is not necessarily determined by the shear viscosity. That's a good question. I mean, in usual turbulence, right? This slope you can predict it based on conservation of Lorentzian integral, for example, or conservation of angular momentum, and based on dimension analysis, you can expect what would be the power law in time and late times, and it's independent of the shear viscosity.
Now, it's a pure ideal fluid statement, but it's just turbulence.
I mean, it is a consequence. You need to have some shear viscosity because in the end, that is what is dissipating the energy.
If that is part of a cosmological spectrum, that will be.
I mean, okay, but this is kinetic energy as a function of time, though. Yeah, not the stuff. I don't know if you're talking about.
You don't lose energy every each.
Exactly. Yeah.
You just transfer it from one moment from one.
You transfer from large scales to small scales, and then you dissipate it at small scales.
Right. But this is integrated over all modes.
This is integrated over all modes. Yeah. This is the total kinetic energy as a function of time. So this is the power law time decay in time.
So this is really dissipation, not cascade.
Yes. Yeah, but it's a consequence of the forward cascading, right, from large into small. If you don't have any forward cascading, you have most of the energy at large scales, so you're not dissipating those scales because your viscosity is at much smaller scales.
No, what I'm trying to say is that if this is the cascade regime, the inertial range, I would expect if you iterate over all modes, I would expect this to be constant and then quickly decay at the scale of the viscosity.
Yeah, but we don't have in this we don't have the velocity spectrum to actually test that. But that's what if you check the velocity spectrum, that's what you should observe. If this is in
no, but does the kinetic energy be constant?
No.
No. But you're constantly sorry. You're constantly dissipating at some scale.
I mean, it takes some time, of course, to develop this, but that's what I'm saying. I would not venture, and we're trying to be a bit careful in the paper to say this is a usual turbulence cascading, right? Because we don't really know exactly, because we also have baroclinic terms and the fractional vorticity, and but yeah, I mean that's what we have in mind as a potential solution for this explanation.
But that slope depends on the value of viscosity.
No. At least in usual, okay. Here we could not test that exactly, right? Because in these simulations we're not using any particular viscosity, right? So what we're having here is mostly numerical viscosity, and we are playing with the discretization, right? So we are also not claiming that this is exactly the slope, but what you can clearly see is that as you increase the discretization, this becomes steeper and steeper. So that's a consequence that this that is telling us that this is really a physical decay of the kinetic energy. If it is exactly this decay, it's something we're really trying to investigate. It's not at the moment completely clear. So, but it should not depend on the viscosity. I mean, usual hydrodynamic turbulence, it does not depend the power law in time on the viscosity.
This is in flat space, not in simulation.
The simulation is all in flat space then. Yes, yeah.
Because you will have extra distribution.
Yes.
The evolution of the unions and like.
That's what we're trying to model here. So So within this paper, indeed, we try to extend what is our understanding of the sunshell model and how the source decorrelates to take into account the decay of the kinetic energy. And what we find actually is the same type of gravitational spectrum that one finds for flat space. For small linear perturbations. But then instead of having this constant kinetic energy and then the suppression factor, which remember it was just the linear growth that then saturates, you need to extend this modeling to an integral over the kinetic energy. And we showed in the simulations that this is exactly what the simulation is following. So as the kinetic energy is decaying, if you integrate the kinetic energy squared over time, you actually find, and this is a comparison of the simulation, is the red dots for different values of the wall velocity. It exactly follows what we find in the simulation. And then here we try to just extrapolate to later times based on the decay. Because in all the simulations, we're already finding a power law in time, which is quite established. So if you extend that to later times, then you can predict what is going to happen in principle if this type of behavior continues, of course. And then you can incorporate the expansion of the universe based on how that decorrelates. Because if this model is valid, then we can also use it because the dynamics of the fluid perturbations are conformally flat after you are done with the phase transition. So that means that whenever we have this power law decay in time, this should also be valid for an expanding universe. I can maybe explain that. If you want, I can discuss that. Why?
The energy is not conserved anymore, and
yeah. But if you're interested, I'm happy to describe that. But it's because you can do a conformal transformation as long as the fluid is dominated by radiation.
Let's say, affecting matter.
Yeah, as long as you're dominated by radiation. Exactly, which at the end of the phase transition is
wavelength very small, probably. You are considering bubble with wavelength very small?
No. So I'm talking about really after so you have an initial fluid perturbations, right? And this is where the phase transition ends. Right after the phase transition, your plasma again becomes thermalized, and you're mostly again dominated by radiation, right?
Yeah.
And this is where we're studying these fluid perturbations. So what I'm saying is that based on these results in flat spacetime, at later times we can try to extend these to also the results in an expanding universe because of this conformal transformation that only applies after the phase transition, not during the phase transition. And if that's clear enough, but yeah, if you're interested, I'm happy to discuss that a bit more. But basically, it's of course just a model that we're trying to do. I mean, one should go into the simulations and include expansion and try to understand exactly what's happening also at later times. But yeah, the interesting part, right, is that for strong phase transitions due to this decay, so what we observe in the simulations is that we are starting to get to some saturation value, right? And if we try to extrapolate this to later times, then we observe that there is not such a large error between what we are already finding and what we expect to have the final amplitude. So this is already giving us a hint of what we expect whenever we have nonlinearities. So the situation is a bit different to what has been used previously, because what I was just mentioning is that you start assuming that you are completely dominated by the linear regime and eventually you saturate. Of course, the system is a bit more complex, and what you have is a transition between the linear regime into the nonlinear regime, and that is because of the decay of the kinetic energy. So we really need to understand for the different cases what we expect as we go into the strong phase transitions. As we go into the strong phase transitions, then nonlinearities start to kick in and give us a and this model can give us an estimate of what we expect to have for the gravitational spectrum. And I think I'm already beyond time, and I was gonna start my second part of the talk. If you want, I can actually.
Journal club now.
Huh?
Pretty sure we have a journal club now.
Yeah. I can stop
the people outside.
Yeah.
Oh, yeah.
Okay.
I can stop the talk.
Yeah, I
here.
suggest we stop, and you can tell us in private to those who are interested, so that we can free the room. So if there are any pressing questions, I think we can ask one quick question.
But you can go to the conclusions.
Okay. So the general problem with 3, no?
Yeah, it started.
Sorry.
You don't want to be
If you want to give a
Well, I mean, but okay, I mean, my main conclusions, right, is that for this part of the talk, is that we have more or less a clear understanding of what happens in the linear regime of perturbations. Then we can have an expectation for the gravitational backgrounds, and we can try to start understanding for particular models or for particular BSM physics how we can put constraints for this with Lisa. But of course, there is still more to be understood from the fluid perturbations. I mean, even already within the linear perturbations, that's not completely clear. I mean, one also needs to map this into beyond the Bach equation of states. If you consider also very small number of bubbles, then you also need to take into account perturbations into the metric tensor. And then as you go into larger fluid perturbations, then we expect to have nonlinearities. This can change what we expect to have. And that needs to really be taken into account. So my main message is that we are almost there, I think. I mean, we have an understanding of what happens for strong phase transitions. We are working also on understanding this for a larger range of parameters and to understand this for different cases. There's also simulations now recently from last year as well by the group in Helsinki, in which they also take into account larger phase transitions also with the scalar field, and they find consistent results. So, yeah, I mean, we need to understand that a bit better if we want to then make good predictions for the gravitational backgrounds. But that's still a bit of an important aspect. And maybe if I just might remark what I was going to talk about in the next part is that this full picture is completely neglecting magnetic fields. Right, this is not taking into account at all magnetic fields. Magnetic field, gauge fields in general, we are of course coupled to the Higgs field, and we expect them to be present. They can also be generated during the phase transition, and that's what was the second part of the talk about, to try to understand what is the effect of magnetic fields, because magnetic fields, they could enhance the production of vorticity. They can really lead to the development of MHD turbulence, and that can really change our picture. So I think that's a very important aspect to take into account, the magnetic fields present during the phase transition or generated during the phase transition. And also what we have been trying to understand is how we can use observations of gravitational backgrounds together with other observations of these primordial magnetic fields to try to make a multi-messenger approach to understand these gravitational backgrounds if they're coming also from phase transitions or from periods of turbulence in the other universe. Yeah, with this I will finish. I'll let you free for those who want to do it. Thank you very much.
We could probably leave the room for the